I want to do another example of relative motion, and in this case we're going to look at an airplane moving in a wind current. So we have some plane, and our plane is given to have an airspeed of 200 miles per hour. And when a problem says a plane has an airspeed, it gives it an object, an idea of its powers of locomotion. It almost always means relative to whatever medium it's in. So if it says it has an airspeed of 200 miles per hour, that means it has an airspeed of 200 miles per hour relative to the wind that it is flying in. So this plane wants to go 900 miles straight east. However, the wind in which it is flying, the air in which it is flying, has a wind which is blowing 80 miles per hour, 60 degrees north of east. Okay, one thing I'm going to do is I've got velocities in mile per hour. The only thing I'm going to be working with is velocities for relative motion, miles per hour. In the end, I want to calculate something in miles, so I'm not going to bother converting to SI. I'm just going to keep everything in the miles per hour units that I already have. So, if I want a picture of this now, I'll get myself a coordinate system here. So let's call plus x this to be east. And so my object is here, and I want it to fly straight east. And so I'm going to be doing something here that's common in these types of examples as well. So I have a sort of a position axis here, but I can draw my velocity vectors sort of the direction that they're pointing on this position axis. So this is the velocity of the plane relative to the ground. If I'm talking about, I want to go 900 miles east, that's a displacement that's relative to the ground. And so if I want to go in a straight line there, that means my velocity has to be pointing in that direction, which is straight east, relative to the ground. Okay. However, I have a wind, and this wind is blowing at a speed of 80 miles per hour, and it's 60, so this theta is equal to 60 degrees north of east. So if this is my positive y-axis, and this is north. So this now is the velocity of the air relative to the ground. And so we know that the velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. That's sort of our notation device here. And cancel those, plane relative to the ground, plane ground, okay. So make sure I get it all worked out. So if I were to draw that, what I want is what direction. I should have said this earlier. I forgot to mention what we're looking for. We want to know what direction to fly the plane and how long it will take to get there. Well, what direction to fly the plane, then, is contained in the velocity vector of that air relative to the ground, the velocity vector of the plane relative to the air. This is the direction that we're going to point the airplane relative to the air. And so if we have this vector here and this vector here, then this vector is going to be represented by this red vector. This is the vector of the plane relative to the air. So we are going to have to point our plane along the direction of this red vector so that the sum of our vector of the plane relative to the air plus the vector of the air relative to the ground gives us the proper vector of the plane relative to the ground that is going to send us straight east to our destination. Okay. So now we need to go about and determine what these vectors are. Let's work in components first and then try to solve it graphically afterwards. Okay, so the vector of the plane relative to the ground, so we don't know its magnitude, so it has some magnitude relative to the ground, but we know that it's in the I hat direction and has no component in the j hat direction. We know that the velocity of the air relative to the ground is equal to 80 cosine of 60 degrees I hat plus 80 sine of 60 degrees j hat. Usually we like to save and plug in these values at the end. These are such simple trigs, I might like to enter those in now. Cosine of 60 is 1/2, so this is 40 I hat. Sine 60 is the square root of 3 over 2, so this is 40 times the square root of 3. J hat gives us a very simple form. I don't have to keep writing V sub A slash G cosine theta over and over again. So, I would say about 95% of the time I save my expressions till the very end to plug in numbers. But sometimes I will simplify earlier if I think it's going to be more convenient for me. Okay. So then we have the air relative to the ground. And so then we have the velocity of the plane relative to the air, which is unknown. We'll just call this v sub x I hat plus v sub y j hat, because these are my target variables. Okay, so we know that the x components and the y components have to equal each other for these. So if we look in the y direction first, we know that, well, the sum of the plane relative to the air plus the air relative to the ground must equal plane relative to the ground. So if we look in the y component, we have v sub y here plus 40 times the square root of 3 here must be equal to 0. Let's make this more transparent if this is not obvious. I want to add these vectors. Let's add them vertically. I know, so the vector of the plane relative to the air, which is vx I hat plus vy j hat, plus the velocity of the air relative to the ground, which is 40 I hat plus 40 square root of 3 j hat. That must equal to the velocity of the plane relative to the ground, which is equal to the magnitude, which I don't know, I hat, plus 0 j hat. Okay, so that's just writing this vector equation vertically, so I can more easily find the components. So this gives me two equations, scalar equations, because the sums of the components must be equal. And so here's one, here's one, and then in the x direction I have v sub x plus 40 is equal to the magnitude of the plane relative to the ground. Okay, well, this I have something. I now can solve for the y component of my vector of the plane relative to the air. That's convenient. So that's equal to negative 40 times the square root of 3. And remember, I'm in all miles per hour because I haven't changed units. And that makes sense, right? There's the y component is going to be pointing negative. Okay, so that's okay. So now I need the x component. Well, here's an equation for the x component, but the problem is I don't know this either. I don't know the speed, so that doesn't really help me. So what I do know, I have to go back to my original problem. What other information do I know that I haven't used? And one piece of information is that my plane airspeed is 200 miles per hour. So that's my speed. The magnitude of the velocity vector of the plane relative to the air is 200 meters per second. I know that the magnitude, and this is the plane relative to the air, is equal to the square root of the sum of the squares of the components, vx squared plus vy squared. And this is equal to 200. So since I found vy, I can use this to find vx. So vx then is equal to the square root of 200 squared minus 40 times the square root of 3 squared. And remember, this minus, this is in fact minus 40. This minus right here comes from solving this equation. This is, if I square both sides, I get 200 squared is equal to vx squared plus vy squared. So vx squared is equal to 200 squared minus vy squared. So that's where that minus comes from. But now I can put this in my calculator, and I get that my Vx is equal to 187.6 miles per hour. Okay, so that gives me my components. So this is Vx and Vy, and that allows me to find the direction because I can find this angle phi south of east that I need to point my plane relative to make this velocity vector. And using trigonometry, that's a right triangle. I know that tangent of phi is equal to the magnitude of the y component, 40 square root of 3, divided by the magnitude of the x component, which is 187.6. I put that into my calculator and I get a phi of 20.3 degrees south of east. Okay, so that's the direction that I need. The final answer was how long did it take? To find out how long it took, I need to find the magnitude of the velocity of the plane relative to the ground, because I know the total distance was 900 miles. Well, I already found a relationship for that. That is given here. The magnitude of the plane relative to the ground is equal to the x component of my velocity plus 40. Which was the x component of the wind speed relative to the ground. So that's 227.6 miles per hour. And now if I just do the time interval, then is the distance 900 divided by the speed, 227.6. And that was, and I'm in hours, so I kept my units consistent throughout, 3.95 hours. Okay. So, interestingly, note that the speed is in fact greater than the speed of the airplane that the airplane can generate. The plane airspeed was 200 miles per hour, but the speed relative to the ground was greater than that because the airplane had a tailwind. The airspeed had a component that was in the direction of the motion of the airplane. So even though the airspeed, there was a slight crosswind in the airspeed, and you pointed the velocity in a direction other than a straight line, the result was a straight line at a speed greater than the airplane itself could generate in a still wind. Okay. So that's the solution to the problem using components. Let's see if we can solve this problem graphically and see if we solve it slower or faster. Okay. So let's go back to our original, let's get a different color. Okay, so this is straight east, and we had this triangle of velocity vectors. We knew that our velocity of the plane relative to the ground was straight east, and then we had, I'll just use these colors here. Actually, I take that back. Let's keep our colors separate. What did I use? Green and red, huh? Okay. So this vector here was the airspeed. This vector here was the plane speed relative to the air. So this is velocity, plane, velocity, plane relative to the air. This is the velocity of the air relative to the ground, where we had VAG plus V plane A equal to velocity of the plane relative to the ground. Okay, so this is our vector diagram. What information do we know about this? We know that this angle is 60 degrees. We know that the magnitude of the green vector is 80. And we know the magnitude of the red vector is 200. The magnitude of the plane relative to the air, that's the airspeed, 200 miles per hour. And we knew that the wind was blowing at 80 miles per hour. So in this triangle, we know two of the sides, and we know one of the angles, which means we can solve for everything else in this triangle using the law of cosines. So if I let, using sort of this to be side C, since I know the angle opposite the red side, then I'll let the green side be A, the orange side be B. I can use the law of cosines that says that C squared is equal to A squared plus B squared minus 2AB cosine theta, where theta is the angle opposite side C. So if I plug these values in, what I want is the magnitude of B. So I want to find the third side at the moment. That's the one I don't know. So if I want to rewrite this in terms of B, I can say B squared minus 2A cosine theta times B plus A squared minus C squared equals 0. So you can see what I've done. I've just rewritten the law of cosines as a quadratic equation in terms of B, which is the parameter I don't know. If I plug in the numbers here, I get B squared minus 80B minus 33,600 is equal to 0. Well, that's a simple quadratic equation. I can put that into, I can solve it just on paper if I want, right? Minus B plus or minus B squared plus 4, well, minus 4AC, so that's plus 4 times 33,600 all over 2. Only the positive of this is going to be a positive number, and if I put this in my calculator, I get B is equal to 227.6. That's miles per hour. The length of that vector which happens to be what we got before. So I know now the length of the vector of the plane relative to the ground, and if I wanted, I could go ahead and solve part B, which is the time it took to go all 900 miles, which is 3.95 hours. The other thing I needed to know was what direction to point the plane. Well, if we go back up here, what I'm interested here is phi there. That's the direction south of east. Well, that phi, using trigonometry, is equal to this phi. So once I find this angle, I'm done. So I can use the law of cosines again, only this time we have this side is C and A and B here. Well, A and B maybe. And so using the law of cosines again, I get 80 squared is equal to 200 squared plus 227.6 squared minus 200 times 227.6 times cosine phi. So I can just solve for phi. If I do all this on my calculator, I get cosine phi is equal to 0.938. I'll carry some significant figures just in case. And then phi is equal to 20.3 degrees, which is the same as this phi, which tells me the angle south of north to point my airplane. So, to each their own, I suppose. But I think in this case, the graphical method was probably a lot shorter than the component method in solving this particular problem. Nonetheless, so I hope we've demonstrated that it's really important that you're familiar with both methods, because for any given problem, one method might be significantly easier than the other, and if nothing else, if the problem is particularly important, you would want to solve it both ways to make sure that they agree if you need to be guaranteed that you're going to get the right answer.